All right, let's get started. So, written exam number one. For this class, written exam number one is most likely going to be, actually a week from today. The decision that I haven't yet made is whether or not it's going to be written and in class, or if it's going to be something of a take-home exam where you're going to do a bunch of analyses. So I haven't decided yet. If it is a written exam, and I'll let you know by this evening by email as well as by Slack, I will let you know which format it will be. If it is a written exam, like I do for all my exams, I allow students to have a 8.5 by 11 sheet of paper on which you can write whatever you want as your notes. I don't expect you to memorize stuff, and you can bring that note in with you to the exam if it is written for reference material. I don't expect you to memorize stuff. And so, as you can imagine, this is sort of an analytical course, and I've done it in the past, and the best way to exercise or assess your understanding of material is to have you analyze something. So I haven't yet decided if it's going to be written in class or if it's going to be something that's take home over 2 or 3 days for which you're going to do some analysis. I'll certainly let you know this evening. My last class today is my graduate course, which lets out at 5:45 p.m. And so, maybe around 7:30 from home, I'll make a final decision and notify you accordingly. So if you're not on Slack, please get on Slack. I'll certainly use both message channels. That is the email through Blackboard as well as the Slack channel. Any questions? All right. So again, homework 2, project 2. That's what I wanted to comment on. So I had a hell of a time trying to get Apple Watch data. I wanted to do some analysis using covariance, variance, and a bunch of other things, correlation on Apple Watch data. There were a bunch of practical issues with that, and so I found some other data for EEGs, electroencephalogram, and I'll be posting that tonight. But as a preamble to that, I wanted to go over some MATLAB to show you a couple things using the actual data that are going to be important for you to go over. So why don't we segue to that before we continue with the substantive material. Okay. So let me minimize this. Let me make that smaller. So let's bring up MATLAB. And this certainly will be with the assignment that I'll post also tonight. If you're curious, the Apple Watch data had heart rate as well as movement. I assume that the data would be aligned, meaning it's the same person taking these measurements at the same time, but that wasn't the case. And it's hard to get medical biometric data easily publicly unless you create it yourself. So this particular data set, the EEG data set, electroencephalogram are brainwave measurements. And I'm not a neurologist or neuroscientist, but nonetheless, you have a bunch of electrodes that you attach in various locations on someone's head, and as you have more brain activity, that gives rise to more neurons firing, and more neurons firing means there are so-called electric potentials that these sensors can pick up. So in this particular data set, it's a publicly available data set on the University of California, Irvine, or UCI machine learning database. It's a popular one, and it came out relatively recently. I think it was 2018 for public consumption. And so in this particular case, you have it's a set of vector-valued measurements. So you have a random vector, so you have more than one random variable. And in this particular case, you have 15 random variables. And so the first 14 variables are the actual measurements from the various electrodes for the EEG, and that 15th and final variable can vary between two values, 0 or 1. If the value is 0, that means the subject's eyes were closed. If the value is 1, it means the subject's eyes were open, and I'll explain a little bit about what that means. So in this data set, it's the result of an experiment where someone was trying to determine purely from the EEG signals if someone had their eyes closed or their eyes open. As you can imagine, right, your brain sends signals to your muscles to open your eyes when you have your eyes open. And likewise, when your eyes are open, you're actively collecting visual data on your retinas and sending impulses to your brain to interpret the scene that you're viewing. And so when your eyes are open, both in terms of the muscles as well as the processing of the visual signal, you're going to get different areas of your brain, a lot more neural activity. And so with this experiment, the creators of the experiment were trying to determine from these brain wave signals, and there were 14 of them, whether or not someone's eyes are open or their eyes are closed. And so they took a bunch of measurements, and they know ground truth whether someone's eyes are open, and they assigned that eyes open state to a variable, that last variable, the 15th one, a value of 1, and they assigned that eyes closed variable a value of 0. So what they were trying to do is trying to use the first 14 brain measurement electrode values, potential values measured by the EEG, to see if they can predict what it means to have your eyes open or eyes closed. And so this type of data set is very typical in machine learning. Machine learning is a subdiscipline of that general branch of computer science called AI. In computer science, there are three main sub-areas. One is called systems, and in systems, you're concerned with the engineering artifacts. So that's like your computer networking, your human-computer interaction, things like your operating systems. The other area, so that's systems, is theoretical computer science. And theoretical computer science concerns itself with a mathematical description of the difficulty for computing something. And so that's your algorithms and your data structures, to a lesser degree data structures, more so algorithms, as well as your computational complexity. Right? Computational complexity, you're concerned about the resources your program uses, memory and time. With algorithms, you're concerned about the runtime, and there are various ways for characterizing that. And then lastly, the third sub-area of computer science is AI. Right? And AI deals with the analytics side. Some people might call it computational intelligence. Where I went to grad school, it was called AI. And so in AI, that's where you have things like machine learning, you have data mining, you have stochastic computing and data analytics and those things. Anything dealing with the analysis and processing of data, be that from files or databases or sensors. And so things that sit there, things like machine learning, robotics, signal processing and stuff like that, voice recognition, natural language processing. And so this sort of data set is very typical of a machine learning problem. And the problem at hand is you're trying to predict the value of one variable, i.e. is the subject's eyes open or closed, based on some other random variables. And it's typically a vector of random variables or a vector of measurements. And so this particular data set, EEG state.csv, and that'll come out with the assignment when it's posted on Blackboard this evening. It has a set of measurements, and it has 14,980 measurements. And typically, when you represent a data set in machine learning, you have it in a matrix format. And for this matrix, each measurement, each vector of measurement is going to occupy a different row in the matrix. So the first row is the first measurement, the second row is the second measurement, and in this particular case, the 14,980th row in the matrix is going to be the 14,980th measurement. And then each column represents a particular random variable or particular type of measurement. And in machine learning speak, you think of a random variable as a so-called feature. right? And together, that vector of random variables or vector of features is how you describe some particular observation of a system. And in this particular case, this system is stochastic, and what you enterprise to do is to describe the stochasticity in a way that you can kind of tease apart the couplings between the variables and see how you can come up with some function for the first 14 variables that will allow you to predict what the outcome of that 15th variable is, whether the subject's eyes were open or closed, i.e. that value of 0 or 1. And so that's what we'll get to a little bit in this class, not this particular class meeting, but this semester, to give you kind of a smattering of machine learning types of things. But the goal for this particular project number 2, will be for you to evaluate things like the average, the variance, but more importantly, the coupling between these variables. Because you can imagine certain regions of the brain are more involved in the maintenance of what you're seeing visually, as well as the muscles involved, your motor control, i.e. those parts of your brain responsible for controlling your muscles, right? And so what you'll get a chance to do is to do this linkage analysis, this coupling analysis on this, and actually report on that. But for the meantime, today, my purpose with going over the MATLAB is to introduce you a little bit to the data set, but also some of the functions that you might need or find useful, as well as talk about how MATLAB implements covariance, which is what we talked about last time. Okay? All right. Any questions so far? No? All right. So this is a so-called comma-separated value file, EEG state.csv, and that wasn't the original name. I renamed it to something a little bit cleaner. And it's called comma-separated value if you've never seen a CSV file, because it exists as a text file, and you could actually read it from the command line with something like Notepad or VI, and it's essentially, in this case, it looks a lot like an Excel spreadsheet. Maybe I'll bring it up in text instead of in MATLAB, because MATLAB is doing some things for you to make it look very nice. So let me bring up command line interface. I don't want that one. New window. Homebrew. Okay, so I'm going to bring this up, and let me go to Dropbox, DSU, classes, fall 2019, stochastic projects, EEG state.csv. Okay, so this is what a CSV or a comma-separated value file looks like. And this is what it actually looks like. It's a text file, right? So it's easy to read. And you'll notice here, I have a whole bunch of numbers, one set of numbers. In fact, there are 15 numbers. Each one of these numbers represents one of those measurements of the random variable. Now I have 15 random variables. The first 14 are the measurements from the EEG sensors. And then that last variable is an integer that can be either 0 or 1, right? If it's 0, it represents the eyes being closed for the subject, and if it's 1, it represents the eyes being open for the subject. And so together we have 15 variables. The first 14 are the EEG measurements, and that last one, the 15th one, represents the eye state, open or closed. Now you'll notice here on the first line we don't have numbers. On the first line we have text, and that text is an encoding of the particular EEG sensor. And I can't remember, I didn't see anything in the documentation about what they mean. That's not as important about what they mean, at least for now. But what is important is that each one of these random variables has a name, right? And so that first line, which is a set of comma-separated text, is the description of what the random variable is for that particular position. And so we start out with this AF3, that would be the first comma-separated value, F7, F3, FC5, and so forth. And you'll see here eye detection is that last variable, the 15th. So there are a total of 15 of them. And it's called comma-separated value because each value, each observation or random variable is separated by a comma. And so you can imagine if you want to read this in, the first thing you need to do is you need to extract the first line of comma-separated values, and there are 15 of them, and each line is going to be the description of what each of the positions, respectively, the first position through 15th position, is going to be the description of what that random variable's name is. So the first thing you need to do when you're dealing with this type of CSV file, comma separated value file, is you need to strip out the first line and partition off each of these values, these strings separated in commas, so you can get each of those 15 variable names, because that's important if you want to print out, variable AF3 had an average of this value. Right? And so once you do that, you take out the header, as it's called, because that's the description for all the other variable measurements. Then line 2 through that last line, that's going to be the actual data, right? The values. So you can imagine at the first time instant on the second line here where my cursor is, that represents the first time instant worth of measurements. This 4329.23, that was the first measurement for AF3. Right? And so forth. I'm not going to go through all of them. The second line represents the second measurement for each of those 15 variables. The third line represents the third measurement. And so in comma separated value or CSV format, each line represents one sample of this random vector. Okay. Any questions about that? Make sense? Yes? Okay. So that's our CSV file. That's what it looks like in the raw, so to speak. But if you load it in MATLAB, MATLAB understands what CSV format is, and it paints this really nice view of it that kind of looks like an Excel spreadsheet. And in fact, if you were to open up Microsoft Excel and you were to open up a CSV file in Microsoft Excel, it'll do exactly this. It understands CSV format, and it'll construct that Excel table, and it will label the headings accordingly. And you'll notice here, across the top, each of these columns were labeled up above with the names that were from the header line of the CSV file. So we have AF3 here, F7 here, so forth. And if we were to scroll over to the last one, you'll notice it says eye detection there. Okay? Make sense? Any questions? So this is a type of CSV file that has a so-called header, right? Not all CSV files are going to have headers, but this particular CSV file has a header. And so when you're dealing with CSV files or comma separated value files in general, one of the first questions you have to ask is, does it have a header or not? And typically they tell you in the data description. Okay? All right. So let me close that. And the first thing I need to do is extract that first line from the CSV file and get the headers. And the headers are a comma-separated list of strings, right? So I need those string names. And so in MATLAB, there's a really convenient function for reading CSV files called CSV Read, but CSV Read assumes you only have data information, that you don't have a header, right? And so CSV Read is going to break if you have a header line in your CSV file. And so the fortunate part is, with the API in MATLAB for CSV Read, you can also specify additional parameters that'll tell it from where do I start the CSV Read. And so in order to get all of this data, because the first line is a header, the first row of that table is the header, I'm going to tell CSV Read, when you read from this EEG istate.csv file, don't start at the first row, start at the second row, right? Because I want to ignore that first row that has the header information. Okay, but I still need the header information. I'm going to use a different function called text scan, and text scan can handle arbitrary data types when you're reading out of a file. So the first thing I do is come down here and I open the data file. And I open that data file using fopen for file open, and it's going to open for read only by default. I'm not going to write to it, but you could write to a file if you wanted to, but we're not going to do that because we're only going to read this data. And so we open the file and we get back this file identifier, and that's just the construct that the underlying system uses to identify the stream of bytes on disk for the file. So then we call text scan, and text scan needs two things. It needs the place from which it's going to read that text, and it needs a format to decide how it's going to interpret all of the characters, all the information that it gets from that text file. So text scan, I give it the file ID that I got as a result of opening the file, so it knows where it's going to get the data from disk, and then I give it a format. And this format, %s, says you're going to read out a string. Now remember, it's comma separated. And so I have a bunch of strings, and one string ends at a comma, and the next string begins after the comma, separated by white space. And so I need to tell it what that data type is it's going to read out of this file, and that data type is a string, right? An array of characters. So that's what that %s is, and you notice, don't actually count, but you have to take my word for it, there are 15% s's here. And there are 15% s's because there are 15 variables that I'm going to read. The first 14 variables are numbers representing these electrodes for the EEG, and that last variable, the 15th one, is a number that can be 0 or 1. So I am going to read out the description. Remember, this is the header file, and I'm going to read it one time, right? So that's what that one means. And delimiter says how these pieces of text are separated is by the comma character. So I have here text scan, FID, the file ID, which is where it's going to get it, the format, a whole bunch of strings, 15 of them. I'm going to read 15 strings one time, and these strings are each separated, i.e. delimiter, by the comma, which is why I have this comma in single quotes. It's the comma character. Okay. Any questions about this? All right. So then also, good programmatic practice. Once you open a file and you're done with the information from the file, go ahead and close back the file. Okay, so let's try this out. So I run this, and I'll set a breakpoint just after it, and I notice headers is a cell array that is 1 by 15, right? And so it takes each one of these and constructs a cell array from each of the strings that it reads. Now, of course, this is a little bit funky, right? I don't want to have to deal with individual cell arrays when I really just want strings. So I call this routine called string, and it says take each one of those cell arrays with the heading for each of those variable descriptions and turn it into a proper string that I can then display. All right, so I do that, and if I look at variable names, and you can actually see the first one is AF3, and the last one is eye detection, okay? So you start out by opening the CSV file, and I know for a fact this one has a header line because that's the structure of this particular CSV. So I call text scan to get the first line and to populate a cell array with each one of those strings that are the variable descriptions for those 15 random variables, the 15 vector of measurements, and then I convert it to a string. Okay. Any questions about this? Make sense? Yes? So now that I do that, now I read the rest of the data table. That's the data portion. That's the second line through the 14,980th measurement, right? So I now use my CSV read, and CSV read assumes that you're going to have all numbers. If you tried CSV read without saying start from the next line, it's going to give you back an error and say, I don't know what to do. This is a string type and not a number. Okay, you'd get an error message. So I call CSV read, I tell it which CSV file to read, and now in this for these last two parameters, when you do a CSV read, how they count things is a zeros-based counting scheme. So the first one starts at 0, the next one is 1, the next one is 2, and so forth. So this parameter 1 that says start from row 1, which is the second row. The first row is numbered row 0, the next row is numbered row number 1, and so forth. So it says start at row number 1, which is the second row, and start at the 0th column, which is the first column. So it starts at row 0, then row 1, row 2, starts at column 0, column 1, column 2. So I want to start at the first column, so it's column 0, second row, which is row 1. Does it make sense? So it's zeros-based counting here for CSV read. When you specify where it starts, it's CSV read. So if I do that, let me do that, and we'll take a look at the data table. Now, of course, if you have a really big data table, it's going to take a really long time to do that read, but for most reasonable data sizes, and this isn't terribly big, it'll just return back pretty quickly. All right, so if we look at our workspace, our memory window, we see a bunch of things going on. Once we read this data table with CSV Read, we got a 14980 by 15 double, right? So when you measure matrices and you give the dimensions of the matrices, the first measurement is the number of rows and the second measurement is the number of columns. So for this data table that I just read in, it's a number. You can think of it as a real value, a double, and it has 14,980 rows and 15,000 columns. Again, the row is considered the measurement and the column is the variable. If I were to double click on that, you'd see here I have each of my measurements from those EEG signals, and then that last one is either 0 or 1. There's some ones in there. There's some ones in there, right? So that's exactly just the data table. And I have 14,980 rows for 14,980 measurements and 15 columns for 15 random variables. Okay. Any questions about this? All right. So now I could certainly compute some things. And when you compute various summary statistics on data tables, it's important to pay attention to whether it performs them for each row or each column. You can certainly change that, but the default behavior is to do it across the columns. And let me explain what I mean. So here I'm calling mean, right? And when you compute the mean, it's the arithmetic mean. It's help mean. And if we look at what it does, it's the mean value of all the elements. If it's a vector, or it also runs on a matrix. Now, of course, when you think about what the mean is, the convention for a data table is that each row represents a measurement. So that means you're going to take all the measurements for the first column, you're going to compute the mean. All the measurements for the second column, you're going to compute the mean. All the measurements for the third column, you're going to compute the mean, and so forth. Now, you might be wondering, gosh, well, how do I compute the mean if I don't know the probability? Didn't you say it was a weighted average? Yes, it is a weighted average, but if you don't know the probability, you assume each one is equally probable. So if you have n data points, each probability is 1 over n. So in this case, we have 14,980 data points, so each one is assumed to have a probability of 1 over 14,980. Okay? So if we compute this mean, it's going to compute the mean of all of those measurements for each column and give you back 15 mean values. Okay, so let's do that. So we step over that, and you'll notice argvals is 1 by 15, right? And so each one of those 15 positions in this vector represents the mean of the first column, the mean of the second column for the data table, the mean of the third column, and so forth. So let's click on that and let's expand a couple of these fields. So we have 4.3 and change times 10 to the 3 for the first column, 4.0 times 10 to the 3, and so forth. And let's look at that last column. Remember, the last column was either 0 or 1, right? And so we had 0.488 is the mean for that last column, representing whether the eye was open, 0, or the eye was 1. Now, granted, this eye open being 0 or 1, the mean kind of doesn't make sense for this, but you can still compute it, right? Because that represents a state like true, false, and not a number that has some real valued meaning to it. Okay. Any questions about that? Yeah? No? Okay. So that's computing the mean, and you can also compute the variance. And the variance, as we said before, is the expectation for a variable that it deviates from its mean, and you square that. So all variance is a positive because you square any negative number and it's going to be positive. And so the variance also works in similar fashion to the mean. It works by taking the variance for each column if you give it a matrix. And so again, the standard or convention is that for the matrix, each row represents a measurement and each column represents a variable. So this is computing the variance for each one of those variables. And you'll notice here we have a 1 by 15. And so the first position represents the variance for the first variable. The second position represents the variance for the second variable, and so forth. So if we look at vars, right, we can see the variance for the first EEG sensor, 6.2, and change times 10 to the 6. And let's look at that last one. Remember, that was either 0 or 1, and the variance is pretty small, 0.2 something, because it didn't change very much. It always was a value either 0 or 1. Okay. Any questions about this? Make sense? So when you compute the variance of a data table, you're computing the variance of each column at a time, and each column represents a different random variable. And here we have the variances of the 15 random variables representing our 15 measurements, or 15 random variables. Okay, so now one of the things we can do is we can say, let me extract all of the measurements for the first variable and for the second variable. In fact, that is incorrect. That's a typo. Let me quit here and let me change that to a 2. All right, just saw that. So when we have this data table, again, each column represents a different random variable. So let me run that. Let me continue. And I take my data table, and in MATLAB, when you use this colon symbol, that's like saying wildcard, like saying star, right? And so what this says, it says, give me the data table. It doesn't matter what the row is, all the rows, loop through the rows, give me set the first column. And what that's doing is giving me all the measurements for the first variable, right? So let's execute that, and likewise, we take all the measurements for the second variable. So now, variable 1 are all of those measurements from the first column of the table, right? So it's 1 by 14,980. And then variable 2 represents all the measurements for the second variable. So if you were going to extract the measurements for a single random variable, you'd just be taking that particular column from the original data table, because down the rows represents all of the measurements, but the columns are a particular variable. Okay. Any questions about this? Make sense? Yeah. All right. So now let's look at covariance. Now, when we construct covariance, we talked about covariance as being the expectation that variable x is different from its mean times the difference between variable y and its mean, right? And we said that was a single value, and it absolutely is a single value. But when MATLAB computes covariance, right, it computes what's called a covariance matrix. And the reason for that is that the covariance that we talked about is just a small part of covariance matrices. And so the approach that they take in MATLAB is they give you the entire covariance matrix. And that's useful if you have more than one variable at a time. The covariance matrix will give you all of the pairwise covariances, because when you compute a covariance, it's between pairs of random variables. But we're only going to do it pairwise at this juncture because we're not ready yet to talk about covariance matrices in this class. Okay? So here, I've taken variable 1's measurement, right? And I've taken variable 2's measurements, the first column and the second column, from my data table. And now I compute the covariance between variable 1 and variable 2. That gives me back a covariance matrix. So let's take a look at that covariance matrix, and let's talk about it a little bit. So in this covariance matrix, excuse me, remember that I computed the covariance between two variables. And in this resulting matrix, you can assume, in this case, it has 2 by 2, it has 2 rows, and it has 2 columns. Now in this notation for MATLAB, whenever it has large numbers, it'll give the base, if you will, of this floating point number, and then it'll multiply by a value in scientific notation. So to get these actual values, for example, in the upper left-hand corner of this 2 by 2 matrix, you see 6.2104. What that value really is 6.2104 times 1 times 10 to the 6th power. Now, it does it this way in MATLAB because it's a lot more compact to display it if you summarize as the multiplication of a scientific notation number times some other floating point numbers. Okay? So what does this covariance matrix say? So let me say covariance matrix 1, 2. Let me bring that up. And let me increase the size of these cells so that you can see all of them. All right. So here we have a 2 by 2 matrix. we have the first row here going across, the second row, and we have the first column and the second column. So if we look at this first row, followed by second row, and this first column followed by second column. If we look at this first row, that first row is the position occupied by variable 1, right? And that second row is the position occupied by variable 2. Likewise, for the columns, that first column, right, is this position occupied by variable 1, and the second column is the position occupied by variable 2. So if I have position 1, row 1, column 1, this is this upper left-hand corner in the covariance matrix, that represents the covariance of the variable identified by the row with the variable identified by the column. So what do I mean by that? Here, I'm in the first row, first column. So that number in that position represents the covariance between variable 1 and variable 1, right? When you have the covariance between a variable and itself, that's just the variance. So that represents the covariance between a variable 1 and itself, or the variance of variable 1, right? Does that make sense? Any questions? No? All right. So let's look at this next position. It's in the first row and the second column. So that represents the covariance between variable 1 and variable 2, right? There's variable 1, it's the first row, variable 2, it's the second column. Likewise, if I go to row 2, column 1, that's the covariance between variable 2 and variable 1, right? And so if you look at that function covariance, COV, and you had x comma y, well, the row number is the x variable and the column number is the y variable. So here, row 2, column 1 is the covariance between a variable 2 and variable 1. Likewise, row 2, column 2 is the covariance between variable 2 and variable 2. When you have the covariance between a variable and itself, that's just the variance. So if we look at these terms here, the diagonal terms on this covariance matrix, those are the variances. So the first diagonal is the variance for variable 1, the second diagonal is the variance for variable 2. Now if you go off diagonal, one of the things you'll notice that in this upper right-hand side, it's the same number as the lower right-hand side. The covariance matrix is symmetric about the main diagonal. So if we go to position 2, comma 1, that's the same as position 1, comma 2 in this matrix, right? And so what does that mean? If I wanted to know the covariance between variable 1 and variable 2, I take in the covariance matrix, I pick out row number 1, column number 2, and that gives me that covariance. Does that make sense? Any questions? Now, if I took the covariance between more than just two variables, I would get more than a 2 by 2 matrix. If I did the covariance among 3 variables, it'd be a 3 by 3. 4 variables, it'd be a 4 by 4. But I just want to start simple with pairwise covariance because that's all we talked about at this juncture. Okay. Any questions about this? Make sense? Yeah? All right. So let's take a look at using this covariance. So here, the resulting covariance between variable 1's measurements and variable 2's measurements, I'm calling covariance matrix 1, 2. Now I just use that big M to represent the fact visually that it's a matrix. You don't have to do it that way, but you want to make your programs more readable. So covariance matrix 1, 2 to just give me this visual reminder that this covariance matrix was produced by taking the covariance between variable 1 and variable 2. Make sense? Yeah. All right. So now that I have the covariance matrix, I now want to pick out the covariance between variable 1 and variable 2. So now I say covariance between 1 and 2, cov 1, 2, is equal to, I access my covariance matrix, and I pick out the first row, because that's the first variable, variable 1, and the second column, that's my second variable. Okay? So I pick out the covariance in the matrix corresponding to the covariance between variable 1 and variable 2. Now, of course, I could have used covariance matrix 2, comma 1. That would have been the same, but I just want to keep the nomenclature standard with the variable choices, right? You could have done it the other way because covariance is symmetric. The covariance of x comma y is the same as the covariance of y comma x, but I just wanted to make my variables match what I'm doing, okay? All right. Any questions about this? Does that make sense? Okay, so now I have the covariance between variable 1 and 2, and there's my covariance, right? Now my covariance, remember, covariance is the product of two things: the difference between variable x and its mean and the difference between variable y and its mean. And so covariance, we talked about that the units can be kind of funky. If we talked about oil production and we talked about gas prices, oil production, the units is barrels, and gas prices, the units is dollars or whatever currency. And it kind of makes no sense if you said, what's the covariance? It's it's 2,900 barrel dollars. Well, what does that mean? It's hard to figure that out. And remember, we talked about correlation, right? Correlation was this fix-up. We divided the covariance by the product of the individual standard deviations, and it gave you something that looked like a percentage scale that varies between 1 and -1. So we're going to compute the correlation coefficient, and that correlation coefficient is going to take our data table, it's going to compute our covariance, and then divide by the standard deviations. Oops, what was that? What is that? That's weird. What is that? Who's doing that? Somebody's like attached to the screen. I think someone's attached to the screen. That was weird. I didn't think you could okay. That was really, I didn't think multiple people could do that. That kind of made me think I had a virus or something. I've never actually gotten a virus in my life, so gotten the flu, but not the computer virus. Okay, that's just kind of, where was I? Oh, yeah. Okay, correlation. So I'm going to compute the correlation coefficient, and it's really a correlation matrix. And similar to the covariance matrix, the positions in the correlation matrix represent the correlation between variable I and variable j. So let me compute my correlation, and you'll see I get a correlation matrix. In this case, it's 15 by 15 because I have 15 variables. And so with my correlation matrix, if I have, I did the correlation over the whole data table just to show you what full matrix looks like. If I take correlation matrix, row 1, column 2, that's the correlation row between variable 1 and variable 2. So let me do that. I take my correlation, and what that says is that the degree of correlation, it's positively correlated, variable 1 to variable 2, and that strength is 0.26, where maximum strength is 1.0, right? And if we look at the correlation matrix, let's see. If we look at the full correlation matrix, core M, and let me increase that. I wonder if that screen share was in this room or some other room, because that could actually be kind of funny if you do it with someone who's in another room. But anyways, one of the things you'll notice here, the correlation matrix, if I look at position 1, 1, the first row, first column, well, variable 1, what's the correlation of variable 1 with variable 1? It's perfectly correlated, right? It's the same thing. So you notice on the diagonal of the correlation matrix, all those correlations are 1, right? Off diagonal, that's where I have my correlations between different variables. So here, row 2, column 1, that's the correlation between variable 2 and variable 1. Right? And you'll notice this correlation matrix is symmetric about the main diagonal. Row 2, column 1 is the same as column 2, row 1, column 2. Right? It's like saying correlation of x, y is the same as correlation of y, x. So if we look at the correlation here in row 2, column 1, that's the correlation between variable 2, whatever that variable is, and variable 1. Right? That's 0.26. But if we look at other correlations, we can see variable 3, its correlation is higher with variable 1. And if we search around here, variable 13, its correlation is 0.99. It's almost 1. It's almost perfect correlation unit step increase with variable 1. So that means variable 13, when it increases, variable 1 also increases some commensurate amount. Now, that means variable 13 and variable 1 are very highly linked with one another. And in machine learning, when you're trying to represent some pattern information, sometimes some of your variables are going to say the same thing. And one of the ways you detect whether two things are saying the same thing, two measurements, is if they're highly correlated. And if they're highly correlated, that means every time I increase variable 13, variable 1 also increases 0.9987. It's not really a percent, but you can kind of think of it that way. So that means I don't need both of them. I only need one of the two. And so one of the so-called feature reduction or dimensionality reduction we do in machine learning is to evaluate the couplings, and then we get rid of the redundancies by saying which two variables are saying the same thing. Moreover, let's take a look at this 15th row. This 15th row represents that state of the eye open or eye close. Now you notice the correlation. Oh, that's weird. Oh, that's -4, because correlation should never be less than -1 and should never be greater than +1. So when I see -3, then I saw that exponent -4. All right, something would have been wrong. So if we see here, this variable eye open, eye close, we'll notice some things are positively correlated. So variable 15 with variable 1, that's positively, but it's 0.01. 0.08, that's negatively correlated. It's a little bigger. This variable 5, that has a really small correlation, smaller than the others, times 10 to the -4. So that means variable 5 does not say much of the same thing as this eye open and eye close. Right? And what am I getting at with that? Well, you need some set of these variables to tell you whether the eye is open or closed. And so one of the things you could do is reduce redundancies, but also if you found some variables that are very highly correlated with this eye open, eye closed variable, variable 15, then aha, maybe that's what I use to make my predictions because it's very tightly coupled. Okay? All right. Any questions about this? Make sense? So imagine then, you had something like an Apple Watch, and that's what I really wanted to do. And you had somebody who has heart disease, and you have a lot of data, and you have your heart rate, you have your EEG, you maybe have blood oxygen content, a pulse oximeter as it's called. So you have these signals in time, and each one of them is a random vector, right? So one measurement is pulse, one measurement is oxygen saturation, one measurement is EEG signal, and so forth. So you have a bunch of measurements. Those are a random variable, so you'd have 3 columns. And let's say you're taking these measurements 5 times a second over the course of some period of time, like 10, 15 minutes. So now you have a bunch of random variables, and then you have this other measurement. Does this person have heart disease? It could be arrhythmia, it could be all sorts of things, right? Could be a heart murmur, whatever. So now the question you might ask is, okay, well, which combination of these things are going to be predictive of someone who has a certain pathology with his or her heart, right? And so you can actually use things like correlation. And it's not just correlation. There are a whole family of methods that you can try to evaluate which measurements are closely linked together. Because if you can find measurements or variables that are very closely linked together through something like correlation and other measures, you can now start to say, what measurements do I need in order to reliably or better predict something else? Okay? All right. Any questions about this? So this is part of so-called dimensionality reduction and feature generation in machine learning. And what we're going to do with the assignment is I'm going to have the EEG data, and then I want you to tell me which variables are most closely, only had 5 hours of sleep, are most closely linked together. Okay? Using things like correlation, and you can tell me stuff about the average and the variance and all sorts of good stuff. Okay? All right. Any questions about this? And certainly this example code will be there as part of the assignment document for you to look over. I'll try my best to post the screencast tonight. It takes me 2.5 hours for each one between the editing and the rendering, but I'll try my best to do that by tonight or tomorrow morning, like early in the morning. And also the assignment will contain the data set in addition to this example MATLAB file. Okay. Any questions? Make sense? Okay. And so at some point, we will certainly use this. Now, classification and clustering is not part of this class. We do that with images and data analytics. But I'd like to add a module on using probabilities to look at clusters of things to kind of ground out and bring together a bunch of the stuff that we talk about this semester. Okay? All right. So correlation does have a purpose. It's a very useful purpose. You can use it to evaluate linkages between variables, and you might do that because you want to get better predictive models in a machine learning algorithm. Okay? Any questions? No? Make sense? No questions? All right, so let's continue on. 1254. Okay, so let me quit here, and let me bring back up the... oh, you know what? Oh, where'd it go? Oh, you know what? I bet you... Yeah, all right. Let me try to stop mirror. Let me restart it. There we go. All right. So when that other stuff displayed, someone took over the screen and mine went away. That's not supposed to happen. All right. Okay. So there we go. All right. So where we last left off, we talked about this property with variance, and it told us what happens when you have an affine or linear transformation on a set of variables. So you have a scale change by multiplying by scalar. So you have a times variable x plus b times variable y plus c, and the identity is goes down as a squared variance x plus b squared variance y plus 2ab covariance between x and y. And so we used a lot of properties. We used distributive law of multiplication of p of xy times each of the factors. We also used the FOIL rule as well. We made use of the associative property, and we regrouped terms, and then we made use of the distributive rule to factor out of the summation. And then once we got that to the last line, we made the observation that we see a variance in the first term, we see a variance in the second term, and we see a variance in the third term, and we got our result. Okay, before we move on, any questions about this? No? So please make sure that you can sit down with a pencil and paper and go through these things yourself. You can't just learn it looking at it. You actually have to participate in doing it, so-called kinesthetic learning. Okay, so let's continue on. And there are other properties of variance and covariance, and I'll leave it to you to go over these. They're standard properties. It talks about the commutative law for covariance. Covariance of x is equal to of xy is equal to the covariance of y comma x, and likewise the correlation of xy is equal to the correlation of yx. Variance. If you take an affine transformation of a single variable, so you take x and you scale it with a scalar by multiplication. So if that scalar is less than 1, you're shrinking it down. If that scalar is greater than 1, you're expanding it out, blowing it up. And then that plus b is shifting it. So it's a so-called affine transformation. So if you make an affine transformation of a random variable, and this affine transformation looks a lot like the conversion from Fahrenheit to Celsius. If you want to convert from Fahrenheit to Celsius, you take degrees Fahrenheit, you subtract 32, so that minus 32 is like saying plus b, right? Addition and subtraction of the same thing. And then that scaling is times 5/9, right? That's multiplying by a scalar. So if you had a distribution for something in degrees Fahrenheit, you don't even have to calculate, you don't even have to actually perform the sampling in Celsius. You just say, aha, I have this property for variance, and so I know what the variance of the equivalent Celsius would be just by this formula, right? So that's why these identities are important. And so we have covariance as well. If you have affine transformation of two variables, x and y, so we say the covariance of x scaled and shifted, ax plus b, y scaled and shifted, cy plus d, is equal to a times c times the covariance between x and y. So if you, for whatever reason, maybe you had degrees Fahrenheit and degrees Celsius, and you want to know what the covariance would be between them, there's your formula. right? You could also, let's say you had a calculation. Let's say you had the relationship between two moving things, and let's say one moving thing was a car moving, and it had a certain velocity, and then let's say you have like an arm on the car, and something is mounted on the end of the arm. If you know the relationship between the thing on the end of the arm and the car, maybe it's at an angle, you can actually look at the covariance between the motion of the car and the motion of that thing on the end of the arm, if you know that relationship. It's an affine transformation. And so these properties are very useful because they save you from having to do all the tedious work of calculating and recomputing the distribution, perhaps getting new measurements. Likewise with correlation, rho, the correlation does not change if you have affine transformations. And so the correlation of x scaled and shifted, ax plus b, and between the correlation between ax plus b and y scaled and shifted, cy plus d, is just the correlation between x and y. So affine transformations do not affect correlation. Okay. And likewise, lastly, we have the covariance between x and y is 0 if and only if the two are independent, right? Independence means there's no coupling. So certainly, if there's no coupling, the covariance is going to be 0. A commensurate increase in x does not affect y if they are independent. And then lastly, variance of x plus variance of y, if they're independent, is just variance of x plus y rather, if they're independent, is just the variance of the individual ones added together. There is no coupling if they're independent. So I'll leave these to you to work through. They're standard properties, very important properties, and they'll make life a lot simpler when you're doing real calculations. Okay. Any questions about this? Okay. So let me do a time check. Okay. So let's take a look at something called Chebyshevs Inequality. And Chebyshevs Inequality is a type of summary statistic, and often it's very useful to know if a random variable is going to exceed some range of values. People do that with stocks, people do that with mechanical parts, people do that with things like piping, like pressure and temperatures, and all sorts of stuff like that. And so, for example, suppose you wanted to know how likely is it for the temperature today to be more than 20 degrees beyond the average. And the question you're trying to ask was something like this: is it way off from what you're accustomed to, right? That's a typical thing you might want to know, right? When you talk about the tolerances of certain systems, what's the likelihood that it'll be worse or beyond what we're used to seeing? And this is the domain of something called Chebyshevs Inequality. And so what Chebyshevs Inequality is, and there's the definition, it says the probability that x is going to differ from its mean, so that's x minus mu, and it doesn't matter if x is bigger than the mean or x is smaller than the mean. If x is bigger than the mean, that quantity x minus mu is going to be positive. If x is smaller than the mean, that quantity x minus mu is going to be negative. So we have this absolute value here to say what's the probability that x differs from its mean by more than some amount epsilon. So is it outside of some threshold? And epsilon is just a constant, it's a number. So we have the probability that x differs from its mean or exceeds its mean by more than epsilon. Probability of magnitude x minus mu is greater than epsilon. And epsilon is just the tolerance, a number you just select. You just pick one. And so that probability is no more than, it can't be greater than, it's less than equal to sigma, the variance of that random variable, over that epsilon. And that's kind of nice. And this actually plays out in reality, right? You could try this out with numbers. If you want to know what's the probability that, temperature is going to exceed the average by more than, 10 degrees, right? Epsilon might be 10 degrees. You take the variability, the variance of your variable, your temperature measurement, you take your tolerance, epsilon, and you could try as much as you'd like. That's going to be the probability. That's the biggest probability at which it'll exceed, right? It's just a basic property. And we won't go into how you derive it. We'll do a basic derivation, but please go to grad school. It gets more simple, to be honest with you, and it gets a lot more fun because you get to pull back the curtain and see why this stuff really works, right? It all kind of folds back on itself. You'll see stuff that you saw back in high school and be like, oh, why didn't they say that? Right? Happens a lot. So anyways, we have the probability that x exceeds its mean by more than some tolerance epsilon is no more than a probability that is the variance divided by that epsilon. So let's take a look at what this means in real terms. And so this bound on probability is a way of saying, does it exceed a threshold beyond what is typical? Now, there's some important examples in the book that deal with portfolio construction as it pertains to stocks or securities. Please make sure you go through and understand the examples in the book. Now, of course, when your instructor says, please make sure you do this, there's a reason why, he or she is saying it. So please make sure that you can understand these examples in the book, okay? All right, so that being said, here we have a typical setup, and this is a probability, no particular probability, but it's a probability nonetheless. Along the horizontal axis, we have our values that we measure for the outcome of random variable x, and along the vertical axis, we have our probability p of x. And that also goes with saying, when you're describing something in graph format, give your audience a hand by describing what the axes are so they'll understand what the graph means, right? So we have these axes, we have our measurements x, and we have our probability y is on the p of x is on the vertical axis, and then we have this red curve, which is our probability. A probability starts out to be very small probability mass, it goes up, and then it goes back down again. In the center, we have our mean mu, and mu looks kind of like the balance point. This is the expectation of this random variable. And now we have our threshold epsilon above and below the mean. So if we have some value x, let's call it x prime here, and let's call it x double prime here, well, the difference between x and its mean, in this case, for x prime, is epsilon. The difference here, in the other case, it's negative epsilon. So if we take the absolute value, that's exactly the threshold that we're referring to for this example for some value of epsilon. Okay. Any questions about the setup? Does that make sense? Okay. So what this upper bound is saying, it's giving us the probability of this colored in red region. So we have probability mass for a probability curve, and that probability mass corresponds to this white shaded region. And what we're asking about when we say what's the probability that x minus mu exceeds that threshold, that tolerance epsilon, what's the probability? Exceeding epsilon is everything that's to the right here, and everything that's to the left here. I'm so used to flipping because like when the board's at your when you're facing the board and versus when the board's at your back, you mentally learn to flip. But I'm like reading this thing and not having my back to the board. So if you go out to the left here, that's where it exceeds on the low end. And if you go to the right here, you're right, that's where it exceeds on the high end. And so that probability that x differs from its mean by more than epsilon is exactly this red shaded region. So what's the probability of those two regions? And what Chebyshevs Inequality says, that probability, the largest it can be, is sigma squared over epsilon squared. Well, that's kind of nice. So you can actually give a bound on how bad it can get. And for something like a stock, if you have a stock or security and you're interested, of course, you want to buy low, sell high, right? That's the theory. You don't want to buy high, sell low. So if you think that this probability is going to be very big, and you can certainly track that for some large enough period of time, if that probability is pretty big, then you could take advantage of that by buying when it swings low, because the probability that's going to exceed it is going to go either on the high end or on the low end at some point with high probability. If you have a security that you're holding on to, maybe you want that probability to be very low, right? Because you want it to be around this region because maybe you want to use the money, but if it flickers up and down too much, you might end up losing money. So you can use these things, these tolerances, if you will, these probabilistic tolerances, to try to make decisions about things that are underlied by stochastic behavior. Now I have a note here called show stock ticker, and I can't remember at all what I was supposed to show. I was going to show you a real stock ticker, but I forgot what I was supposed to talk about. So I'm going to skip that. If I remember another time, I'll bring it back up in a different module. Okay, so you really don't remember. Okay, so let's see if we can get to Chebyshevs inequality. And I'm going to pause a little bit here, checking for time, to make sure that you really understand what's going on here. So we have Chebyshevs inequality, and what we want to get to is basically this expression, and we're going to start with the variance. Recall the variance was sort of adding up a probabilistic average of all of the spreads above and below the mean. So let's draw sort of a prototypical probability. Oh, my penmanship's getting better. And, it might look like this. And so we have our mu, our center. Here's P of x. And here's x. And we have some values of x. Let's call that x prime, x double prime. And so we said the variance is the difference squared that x has from its mean, each value x, and we take the probabilistic average. So we take this distance and we square that, and we take this distance and we square that, and we weight these sums together, that distance squared, we weight them together by the probability, P of x double prime, P of x prime, and so forth. So this is how much this graph is dispersed in this direction about the mean as well as in that direction. If we have two graphs, two probabilities, and one is kind of very spiky, right? And then we have another probability, and maybe that is kind of more smoothed out, well, the variability of the first graph is going to be less, the variance is going to be less than the variance of the second graph. Second graph is spread out more. So all of these weighted sums of the difference between each value x and the mean, because you have more x's further out here, above and below the mean, that's going to be larger variance, right? Okay. So if we take this expression, okay, we're going to do a little bit of fix-up. First, any questions about this so far? All right, I don't think I'm going to finish today, so I'm going to find a good stopping point and we'll pick back up on Tuesday. So now what we're going to do, we're going to make a true mathematical statement. We're going to take our equation for variance, and now we're going to limit the x's for which we compute the variance. So before, when we computed the variance, we talked about all the x values above and below the mean. So we had this x, we had that x, we had that x, and so forth. Now we're going to limit them, and we're going to limit them only to x values that are outside of a region that's epsilon below and epsilon above the mean. So instead of all of the x's, we're only going to consider those x's that are here to the right and those x's that are here to the left. And we're still going to compute the variance, but not for all of the x's, only for those x's in a certain region. So if we're computing variances, yes, we're adding up distances, but now we're excluding some distances. We're excluding those distances that are in this closed region within plus epsilon and minus epsilon above and below the mean. So that's what this expression is. We're changing the loop, see, I'm so used to implementing it. We're changing the summation. And the summation is saying, I'm not going to sum over all x's, I'm going to sum over some x's, and it's only going to be those x's that are more than epsilon away from the mean. So if I do that, that means I'm adding up fewer of these distances. If I add up fewer in these distances, it's going to be smaller, right? So here we have this original expression for variance is greater than or equal to, which is a true statement, the same variance expression, but on a smaller number of those x's. Does that make sense? Okay, so that is absolutely a true statement. I have not violated the rules of mathematics. Okay, so let's now take this expression. We're going to make a further limitation. So now I say, okay, well, here I have all of those x's that are more than some epsilon away. So what I'm going to do, I know that x minus mu is limited to those x's that are more than some epsilon away, right? So I'm just going to replace this with epsilon, because if they're more than epsilon away, I have my mu here, I have my epsilon distance, all of those x's, there's an x, that are more than some epsilon away. if I just replace this distance with epsilon, epsilon is the smallest that distance can be, because these are all more than epsilon away. So if I just replace x minus mu with epsilon, so I say epsilon squared instead of x minus mu squared, I know that that equivalent expression is less than the previous one, because I'm limiting even more. That makes sense? Any questions about that? So now I can say, well, my original variance is bigger than this expression where I limit my x's, and if I replace this x minus mu with the smallest value it can be, this expression is greater than or equal to now this equivalent expression. Okay? So we will stop there. It's about 30 seconds left, and we will pick back up with this on Tuesday. All right. I'll try to post this tonight, and I will see you all on Tuesday. And please look out for the email. I will post the data set and finish up running the assignment. It took a long time, but it is real hard to get Apple Watch data from someone else. And I'm not going to let you analyze my data. So I don't have an Apple Watch. All right, I'll see you all on Tuesday.